All right, welcome to Module 9 class, or as the kids say, FAM, on statistical data. And it's called Reintroduction because I'm pretty sure you all have to take statistics, or at least some form of statistics, in order to get into the program. So this is kind of a refresher, I suppose. But you'll be learning a lot of skills here that'll be useful. So either way, welcome. In this lecture, we're going to be figuring out what the heck central tendency is and how dispersion works in statistics. We're going to learn how to define different variables in statistics. We're going to go ahead and look at statistical parameters. Some of them we talked about already. We'll be going over them again. And then finally, we'll be looking at calculating some of these measures and using them in terms of clinical reporting. All right, so like with every lecture here, and I don't know if any of you noticed this, but in my lectures, I have a bunch of these AI pictures, and they make me chuckle because at least when I did this, I'm sure the AI is better now. There's a bunch of misspellings in there, and I just don't care. So if you find a misspelling, it's almost like an Easter egg. So enjoy them as we go through. Anyways, our case for this lecture is going to be this clinical dilemma. Really, despite completing required statistics coursework during your undergraduate studies, you found that much of that knowledge has faded away. The formulas, concepts, and applications that once seemed familiar now feel distant and unclear, a little hazy. So now you need to figure out how to rebuff that. You need to brush up on your skills, okay? Because you're going to be required to interpret complex drug literature and randomized controlled trials and make evidence-based recommendations. And this all stands on the foundation of knowing statistics, at least having a strong enough foundation where you can talk in statistics. So here's the opportunity for today. Take this and try to build off what you remember from your undergrad work and make it useful to yourself so that not only can you get an A in this course, but you will be able to excel throughout the rest of the time here in your PharmD program, where you'll be seeing lots of statistics over and over again. To start your reintroduction to basic statistics, let's start with the foundations. That consists of central tendency, right? When we use measures in data reporting called statistics, they generally are used to identify the center of the data, mean, median, okay? And so then you need to also describe the dispersion of the data. How spread out are they? Is it really, really wide? Is it really, really tight? Using confidence intervals, for example, or other statistical techniques. And then finally, you need to be able to classify the variables to be able to apply certain tests to them. Okay, so different data types require different tests, which you'll learn about, and we need to be able to identify those. There are really two types of statistics. One is descriptive and one is inferential. So descriptive is what it's called. You're just describing the data. You're describing the central tendency and mean, median, mode. You're describing the dispersion in terms of a standard deviation, error, interquartile range, things like that. Maybe you're doing frequency distributions and percentages for other types of data that we'll talk about. And you can use it to characterize study populations, right? You're going to give that in those group comparisons for the baseline statistics we have already talked about. That's where you're using these types of statistics. Inferential statistics, on the other hand, are those that are analyzing the thing you want to report on, the exposure and the outcome specifically. Okay, so hypothesis testing, we talked about p-values and confidence intervals. Now we're going to talk more about statistical tests that derive those p-values, like t-test, ANOVA, chi-square, and Mann-Whitney U, whatever else you want to talk about. Fisher's exact test. There's lots of tests. And so what are they used for? To assess differences between the treatment groups and report them in a language of statistics that can be understood readily. Okay? And it helps determine if findings are likely due to chance. Remember, there's always random error in the data set. And so this is what inferential statistics helps you to minimize or rule out. Let's get down to some classifying of variables. First, quantitative variables. So what is a quantitative variable? It's basically a numerical data point. It can be counted or measured precisely. Okay? And so these are what's basically the foundation of pharmaceutical research because they're objective. And these are common things you think of: age, weight, blood pressure, cholesterol levels, BMI, glucose levels, all those are quantitative variables. In contrast, you can have qualitative variables. These are non-numerical data expressed in words or categories. They're less common in medication studies because they just don't provide that objective measurement that doctors like to see in these reports, but they're still valuable for understanding patient experiences. And things we see with qualitative variables could be like interview responses or symptom descriptions or patient narratives. So those would be qualitative variables. Quantitative variables can be further broken down into discrete or continuous quantitative variables. Discrete variables are generally represent categories or count. They have discrete kind of bins they have to fall in. Okay, there's a limited number of possible values. They often are whole numbers in nature. So things you could think of as like sex for male and female. Those are discrete categories. Mortality, you're either dead or you're alive. Discrete categories. Pregnant, you're either pregnant or you're not. Discrete categories, okay? That's why they're discrete variables. They're usually counted rather than measured, versus continuous variables are measured, okay? Measured with instruments. They have an infinite theoretical range. They can include fractional measurements, and we usually see this, like the big one we'd always think about, weight. You should go right to weight. Weight theoretically has no limit, okay, so it's a continuous variable, and you can measure it you could either measure it in whole numbers or all the way down to fractions of a pound, and so you can get very exact. Those discrete variables usually can be broken down further into nominal or ordinal data. So nominal would be like that sex I talked about, so male or female. Nominal data means that it has yes or no to it. It's binary in nature. Okay? Versus ordinal data usually has more categories. They have a natural sequence. We usually see these with surveys, so like a pain scale from 1 to 10. And you can see there's different statistic types, which we'll talk about more in the upcoming slides about how you use depending on the data type. This is why it's so important to classify variables, because it tells you exactly what statistical test to use. You can further classify variables with interval and ratio data, which generally apply to continuous type of data. And so interval data is basically you have the same distance between each of the points, but there is no true 0 point, meaning there's no null. 0 point is arbitrary. So temperature, 0 degrees Celsius doesn't mean there's no temperature. It's just a type of temperature. But 0 to 100, each of the spaces means it's an equal increase of 1 degree Celsius. In contrast, ratio data is interval data, but it has a true 0 point. So things like all the biological measures we talk about, drug concentration, they have a true 0, meaning there's 0 drug concentration. But everywhere a drug concentration from 0 to 100 has equal spacing on the way up there. All right, here's a little handy table for you that I would use if I were you to study to help you remember discrete versus continuous and all the other subtypes, nominal, ordinal, interval, ratio data that comes with it, and some examples and mathematical operations that you can perform on each of these data types. Returning to measures of central tendency, how do we do that? Those are the three main ones you probably learned about in high school: mean, median, mode. Mean is the arithmetic average, right? You add up all the values and then you divide by the number of values you added up. Okay? This one is sensitive to outliers and can be skewed. So if it's what's called skewed data or non-parametric data, we have to use a certain type of test for that, or a transformation. Median is where you would use for skewed data. Okay, it's the middle value when you arrange all your values in ascending or descending order. Okay? And then if you have an even number data set, remember, you have to take the average of the two middle values. That's the sneaky part of a median that you probably were tested on the ACT or the SAT. And then finally, mode is the most frequently occurring value in the data set. You almost never see this one, but you can see it sometimes, especially with reporting common adverse effects of drugs or for a drug class. We can just demonstrate what happens with outliers by looking at this example of what happens when you add an outlier to the mean versus the median. So you have a sample data set here with 7 individuals, the mean is 68 and the median is 69. And then you replace one of those person's heights, okay, with Yao Ming's height. He's super duper tall, right? And he's going to skew that data set to the right. So the mean shifts dramatically. It goes from 68 to 71. That's a 3-inch increase, which is pretty big for height. So that extreme value really pulls it to the right, while the median remains the same. So it shows you when you have skewed data that a median is very useful because it's relatively resistant to this skewness that occurs. So often when you have what's called non-parametric data or skewed data, you will see things reported instead of means and standard deviations, you'll see medians with interquartile ranges. And this is the reason why. We've taken a look at some of the ways to measure the central tendency of data. How about dispersion? Well, these come in mostly 3 different flavors, I would call them. One would be the range, right? Looking at all possible values from minimum to maximum. So the range is maximum minus minimum. The interquartile range, which is looking at all the numbers between the 75th percentile and the 25th percentile. So the middle 50% of the data. That's the interquartile range. And then finally, variance and standard deviation. Essentially, these are mathematical equations to characterize the dispersion of data, and it's very commonly used. Standard deviation especially. You'll see this with continuous data, and it serves as the foundation for many statistical tests. The nice part about some of the methods to look at dispersion is you can visualize them very nicely. And so this is where we see the classic or common bell curve that we all hear about from statistics. And we generally see that when we're looking at standard deviation. So the bell curve is basically a bell in the middle and the tails go out more closely to the x-axis. And so what it's showing is that most of the data ends up in the middle around the mean or the central tendency. And then you have less and less data as you go out towards the tails. And so this can actually be mathematically shown where 68% of the data falls within one standard deviation. So in the graph at the top, 68% would be those dark blue bars on either side. That's 68% of the data. 2 standard deviations is 95% of the data, so adding in those slightly lighter blue bars. And then finally, 99% of the data falls within 3 standard deviations, which would be the light blue bars at the end. And then everything else is certainly going to be very much away from the central tendency or the mean and would be considered extreme outliers. Now that we have central tendency and dispersion under our belts, as kind of an idea of how data spreads itself out over a mean value, let's transition into diagnostic tests. So this is really important because this is always confusing for students. So try to, go over these slides a few times and understand sensitivity versus specificity. So what is a diagnostic test? It's a tool to identify disease presence or absence. So anything that we use to measure on patients, anywhere from an MRI test to glucose to blood pressure for identifying hypertension. And every test has sensitivity and specificity with it. Sensitivity refers to the ability to correctly identify those with disease, so a true positive, versus specificity refers to the ability to identify those without disease, so a true negative. Sensitivity, true positivity, specificity, true negativity. And basically you can get predictive values from these measures to give someone the likelihood that they have a disease given their test result. Let's take a look at how diagnostic tests break down within an HIV example. So here we have a 2x2 table where we have on the left someone that has a positive HIV test versus someone with a negative HIV test. And then at the top you would have someone who actually has HIV, so it's present, versus someone who doesn't, it's not present. And so you can see in this 2x2 table, you have 4 possible scenarios. A true positive where someone actually has HIV and the test identified it appropriately. A false positive means that the test says someone has HIV, but they don't have it. Then a false negative, where the test fails to detect HIV in someone that has it. And then a true negative, meaning that the person doesn't have it and the test correctly identified that they don't have it. Now that we understand the background of a diagnostic test, where are they used? And basically, they're used to help make clinical decisions. So they provide objective data to complement one's clinical judgment. So they identify patients that might have a disease, okay? But they always have to balance accuracy and practicality. There is no perfect diagnostic test. They don't have 100% specificity and sensitivity. That doesn't exist. And even the really good ones are more costly than insurances will pay for, or be too much burden on the system, or they're more invasive and they have more complexity to run. And so we need to always balance this. So the clinical judgment with the diagnostic test value. And so the performance metrics of tests are basically evaluated on their sensitivity, specificity, and predictive value. But each metric will address a different clinical question depending on the scenario. So maybe you want to rule out a disease in a patient, or you think they have a disease, and you want to see if they have it. All these come into play when the doctor orders a given test. Let's take a look at these metrics and how they're useful in different scenarios. So you have sensitivity, that would be the true positive rate. It would mean the proportion of individuals with the disease who test positive. So they're really useful when you don't want to miss someone who has a disease, okay? And SNP is sensitivity is positive. That'll help you remember it. The formula is true positives divided by all disease patients. That would be the proportion who test positive. And obviously, they're usually used for screening, and they prioritize sensitivity to minimize missed cases. In contrast, specificity means it shows true negatives when they're actually negative for a disease. Okay, and high specificity will help avoid false alarms. You don't want to freak patients out. You don't want to have to order a bunch of new testing that was unnecessary. So maybe you want to test with really high specificity. And you can remember this versus SNP. This one's spin. So specificity is negative. And just like the other formula, it's true negatives divided by all non-disease patients. And it's usually used as a confirmatory test to prioritize specificity to avoid unnecessary treatments. And then finally, we have positive predictive value. And really, that's looking at the likelihood of disease based on test results. So it indicates the probability of a disease given a positive test. Well, a negative predictive value indicates the probability of no disease given a negative test. So it kind of incorporates sensitivity and specificity, whether you're looking at positive predictive value or negative predictive value. And you can see those calculations there as well. True positives divided by all positives, true negatives divided by all negatives. And it just gives you another layer on top of sensitivity and specificity to understand how useful a given test is. Let's break all these down into a 2x2 diagnostic test table to help you really kind of put all this information together. And then we'll look at the equations on the next slide that'll help you calculate this. So you have a diagnostic test result on the left, positive, negative. And then again, you have disease actually present and actually absent in the top row there in the second and third columns. And then the totals are at the right and the bottom. So each cell then represents a different combination of test results and disease statuses and allows for easy calculations, which we'll see on the next slide. Once you set up that 2x2 diagnostic table, then you can start doing calculations fairly easily and really help facilitate and kind of demystify sensitivity, specificity, positive predictive value, negative predictive value. And so we can see here, I'll go over two examples. With the sensitivity calculation, it's A divided by A plus C, which is that total number. And this should kind of chime back, or at least remind you of doing incidence and prevalence types calculations. So if 45 of 50 patients with a disease test positive, then the calculation would be 45 divided by 50, which is 90%. In contrast, when you want to do the positive predictive value, then you're going to do A divided by A plus B, which would be, instead of all disease patients, it's all positive test results in the denominator. And so if 45 of 60 positive tests are true positives, then 45 divided by 60 gives you a positive predictive value of 75%. So again, sit with these terms and look at these calculations so you can better understand sensitivity versus specificity and positive predictive value versus negative predictive value. One critical element in studies is statistical power, which is often not reported in a lot of studies. Generally, they are required when you do a randomized controlled trial because there's a big checklist when you publish something in a journal, and statistical power is generally in there. And usually statistical power is seen in grants where you're trying to get money to do a study because they want to know how many patients you want and if you're going to have the statistical power. And why is this so important? Because basically it tells you if your study has enough power or the ability to detect a true effect if one exists. So if you don't collect enough patients and your study is underpowered, you might not be actually detecting an effect that's there. And that's really important for interpretation when we read these studies. So looking for power analyses, or at least a report of the power and whether or not their sample size met that pre-established power, is always a critical element of evaluating a study design. Power always comes into conflict with ethics in research, and we'll see it with an example here. So pretend that I had a pill called Research April that helps students do better in PHA 4125. And so I want to do a double-blind placebo-controlled trial of over 15 weeks over the drug lit course and see if students who took the pill do better versus those who got placebo. But the problem is testing an unproven medication in humans could be very risky, and you're just basically subjecting participants to unknown risks. And so we want to use the smallest sample size possible to minimize those risks. But then statistical reality comes in through the back door like the Kool-Aid man and says, boom, you might not have enough power now to actually detect an effect. So we're stuck between a rock and a hard place where we don't want to test this in too many patients because what if we kill a bunch? Maybe that's the worst side effect. I don't know. Versus we want to have enough statistical power to actually detect a true effect. So these two concepts are always in tension in research, not to mention the logistics and the finances of doing larger sample sizes. We've talked in previous lectures about random error and how we minimize biases and all of those things that we want to try to avoid in studies. So I put this back up here to remind you about how hypothesis testing always uses a structured approach. You state the hypothesis, formulate the null, establish a significance level to prevent that random error from creeping in, collect and analyze, draw conclusions. And so this is important to remember this as we understand how statistics will be used to prevent certain types of errors with hypothesis testing. We mentioned some of these errors in our previous study on bias and random error, but let's go into depth here with it. So usually statistical errors occur in two different flavors. And this 2x2 table will help you remember this. So on the left, we have do not reject the null versus reject the null. Okay, and that's what the statistical test tells you, versus at the top tells you the null hypothesis is actually true, so there's no difference, or the alternate hypothesis is true. There is a difference. And so when the statistical test tells you do not reject the null when the null is actually true, you have correctly failed to reject the null, meaning that you found no difference. There's no error. Versus if the test tells you do not reject the null hypothesis, well, the alternative is true, so that you're saying there's no difference, but there is a difference in your study. You've fallen into type 2 error, which has to do with the beta value. The null should have been rejected. Your study was not powered adequately. In contrast, when you have reject the null hypothesis as your statistical test interpretation, but your null hypothesis is actually true, you're falling into a type 1 error, which is an alpha issue, which we kind of talked about in a previous lecture. The null should not have been rejected, but now it's been rejected. And so you have what's called a false positive, right? You think you've found a positive result in your study, but actually it should have just been a negative. And that's in contrast to the type 2 error we just saw, right? You said there was no difference, but actually, truly, there was a difference. So you has a false negative. So write that in there. Type 2 error is a false negative. Type 1 error is a false positive. And then finally, if you have reject null hypothesis determination from your test, and the alternative is actually true, then you've correctly rejected the null and there is no error. So with these types of errors, where does power come in? Well, the power definition of power is basically the ability or the probability of a study to detect an effect when one truly exists. So think about how that goes back to sensitivity and specificity. That's why we went over this first. And so it represents the likelihood of correctly rejecting the null, meaning having a true positive result, and it's calculated as 1 minus the beta value. And in general, standards for doing studies say that you have to have at least an 80% powered study. So a beta value of 1 minus 0.2 is 80%. But really, you probably have 90% or higher, meaning that you need higher sample sizes. And there's various software and online calculators. You could just put into your favorite search engine power and sample size or sample size calculator, and everything will pop up. And the reason this is so important is because low-powered studies waste resources, they waste participant time, they waste participant pain and potential good effects and risks to not answer the question of interest. So establishing a high enough level of power and meeting that over time is critical to a study meeting its endpoints and having interpretable and useful results. Now that we know what type 1 error is, which has to do with alpha, versus a type 2 error with beta, how do we use these to put together a sample size determination? How do we know how many patients we need for our given study? And so it uses these 4 elements. It uses the type 1 error, which is usually set at what? 0.05, that's right. And then a type 2 error, we have to set into the calculator, which usually uses 80%, okay? And then you have to figure out your event rate and your effect size, okay? And so these usually you have to guesstimate based on your expertise, or you go into the literature and find something comparable that you can put into the calculator. And so for the event rate, when you have a really rare outcome, as you would expect, you need a larger sample size, right? Because it's a rare outcome. And when you have smaller differences between groups, that means you need a more precise estimate, which means you need a larger sample size. So all these things are in an ebb and flow and a power calculator to help you determine how many participants you need in your study to figure out and have a minimization of these type 1 and 2 errors. Usually you do these sample size calculations before you begin the study and before you even get funding, but sometimes researchers just do them after the fact, maybe on a pilot trial, and to let readers know that their study was adequately powered despite being a pilot study. So let's see what happens to sample sizes when you play with the outcomes in each group and the type 2 error rate. So in the top row, you have outcome and control group, and the outcome can be 1%, 5, 10, 20% going to the right. In that first column on the left, you can see the outcome in the intervention group being 2, 10, 20, and 40%, and it's varied for the type 2 error rate, okay? The type 2 error is becoming more or less powerful, it's becoming higher as you go down in each of the columns, 10%, 20%, and 50%. So you need reduced sample sizes when you have a higher error rate, meaning a lower power. So let's start with the outcome of 10% in the top row for the control group compared to the outcome of 2%, that first row, in the intervention group, with an error rate of 10. You can see the sample size is 3,696. Then if you compare those two outcomes between the groups, 10 and 2%, but you want to have a lower type 2 error rate, meaning, or a higher type 2 error rate, meaning a lower power, you need a lower sample size because you're allowing for more error. And then the error becomes too large to even have a number in there. Let's compare that to the outcome of 1% in the control group. So at the top 1%, and go down to the first number there, which would be the outcome in the intervention group at 20%, is 62. Did you find 62? And so that 62 number is how much sample size you need to have a type 2 error of only 10%, okay, which would be a power about 90%. versus if you lower the power in your study and you're allowing for more type 2 error, you can have a reduced sample size of 49. And then if you're allowing a lot of error in your study, you can have a reduced sample of 29. So what this is showing you, and look at each of these here, is that as you allow more type 2 error rate, you can have smaller sample sizes. That's the takeaway here. You can allow more type 2 error rate, you can have smaller sample sizes. The more reduced error rate you want, the higher sample size you need. And you can see some of that from that table here in words. So what are some factors that affect sample size requirements? Factors that increase the need for sample sizes are smaller event rates, which we already saw. If you have a rare event, you're going to need really big samples to find that rare event. If you have small effect sizes between the groups, meaning that they are different, but they're really close, then you're going to need really precise measurements. And how do you get precision? You need more sample size. If you want high power in your study, you're going to need larger sample size, and higher power decreases the type 2 error. And finally, if you have really high variability in the measurements, whatever your outcome is between the groups, maybe like blood pressure or glucose, if it's really variable in the populations you're studying, you're going to need more sample to help hone in that variability, to find the central tendency, right? To minimize that dispersion and to actually find the true difference. So that's why you need bigger sample sizes. In contrast, if you have a higher event rate, then you might need lower sample sizes, meaning that you're studying something that happens really, really commonly in the population, maybe a side effect from a drug that happens in 50% of patients. You won't need that many patients to find it, right? Because you're going to find it in 1 of every 2 patients. If you have large effect size that are really dramatic, like treating someone with a medication that lowers heart attack risks by 80%, that's a huge effect size. So you're not going to need a very big sample to see that effect. Large effect size, lower sample size. If you want to study something with lower power, maybe you don't have the money or you just want to do a pilot study, then you can get away with lower sample sizes because you're allowing more type 2 error to creep in. And then finally, crossover designs, although very difficult to do, are highly useful for this because it increases power. When the participants serve as their own control, right? If you serve as your own control, you yourself are equal to you yourself. So the between groups that we usually see in the demographic comparisons table is not relevant to a crossover design because a patient serves as their own control, allowing for drastically reduced sample sizes. Okay, so where do we go from here with this lecture? I want you to really know your variable classifications. I want you to know how do we look at diagnostic tests and interpret them. So you should know sensitivity, specificity, positive and negative predictive values. Know them, know them, know them. They're confusing, so look over them again. Make yourself note cards. And then finally, how are these types of false negatives, true negatives, false positives, true positives relate to sample size and power calculations, alpha and beta? These are all things that you should be aware of as we go forward in this course. And again, you'll see it here. We're going to practice this in our activity in terms of classifying variables and looking at diagnostic tests and sample size considerations. Thank you.